So far, we've learned that all matter is made up of atoms, and because of Rutherford, we learned that the atom is mostly empty space, and a small, dense nucleus lies in the middle, and electrons are on the outside. But until this point, we don't know too much about what those electrons are doing. Well, Bohr gave us a little bit of light on that. And a lot of that is based on atomic spectra, like this one for hydrogen. And if you take a gas tube of hydrogen and put some energy into it, probably electricity, and look through a prism or a spectroscope, you'll see 4 lines, a red, a blue-green, and 2 kind of purple-violet lights. And no matter where you get your hydrogen, whether it's in a star or in a tube on Earth, you're always going to get that signature for hydrogen and only for hydrogen. So Bohr's model helped explain that. And let's start by looking at this model on the left. These 4 lines come from, in short, when an atom like hydrogen is excited, the electrons actually move from what's called the ground state up to a higher energy level. And these he put up to level 7, but they could go up to infinity. And the key to this is, well, there's 2 keys. Number 1 is there are certain allowed energy levels. So if the electron could go anywhere, then we would see a whole rainbow of colors in the spectrum. But because there's only certain allowed energies, we see that when the electron falls back down to a lower energy level, we're going to get only certain wavelengths of light. So allowed energies. Another important part of this is these energy levels 1, 2 through 7. We still, even though we don't use the Bohr model that much, we still use these energy levels. So the ground state is the lowest energy levels. So if you have just your typical atom sitting around, it's most likely in the ground state. And then if you put some energy into it, it'll be in the excited state. So just filling in down below here, the Bohr model was able to explain the hydrogen line spectrum. And when energy is added, it'll jump to higher energy levels known as excited energy state. And then when this excited electron falls down to, it doesn't have to be the ground state, but any lower energy level, it'll release energy in the form of a photon of light. So as you might imagine, these photons are going to be different colors based on how much energy they have. The larger the gap in the energy levels, the larger the energy of the photon. Kind of makes sense. Therefore, as we learned, the higher the energy, the shorter the wavelength, and the higher the frequency. So these spectral lines are emitted when the electron falls. When an electron falls, it goes to a lower energy level, so the energy has to go somewhere. It's shot out as a photon. Since the spacing between the energy levels is constant, you'll always have the same energy and wavelength. That's my sign for a wavelength. So it looks to me on this chart over here like there's a lot more than 4 lines. Well, we actually only see 4 of the lines in the Balmer series. So the red, the blue-green, and the 2 kind of purple-violet. So even though there's 5 here, we can see 4. But it looks like the Lyman series is higher energy. these will be in the UV range because they're higher energy than violet. And these guys over here will be, as you might imagine, in the infrared range. So you can see those, but only with a detector. We can't see it with our eyes. In the next page, you can see how this works. We have our gas lamp over here. The light that's discharged is going to be, for hydrogen, kind of a purplish red light, but then it splits into these 4 lines that we see when we look through a spectroscope or through a prism. And then here are the 2 purplish ones. These would be the highest energy of the visible, and this red line down here would be the lowest energy. So this transition, if you go back to this earlier Bohr model, if you look at the 7 to 1, it turns out that the red light comes from the 6 to 5, and then this purple light over here comes from the 6 to 2. So when an electron falls from energy level 6 to 2, it's going to have more energy than the one that falls from energy level 6 to 5. And if you're wondering why we don't see the 6 to 1, it's back to the ground state, because that's going to be in the ultraviolet range. We can't see that one. So the take-home message from this is that every element has its own fingerprint. And this tells us a lot about how electrons live in the atom. So there's a lot of different energy levels, especially when you get to these bigger atoms. And every element has its own fingerprint where the electrons can go from one level to another. Those levels are actually in different locations for each atom. So the other take-home message is that this only works for hydrogen. So Bohr's model is great. It gave us an initial look at one element, but it doesn't work. It falls apart when you talk about different elements.